Okay, so let's say that we had 2 points on a grid like that were not lined up horizontally or vertically. We could take the Pythagorean theorem and apply it in this case to help us find the distance between them if we construct a right triangle that meets those points. And if we did that, we would end up with this side down here being our side that is our A side. This side could be our B side, and then this side would be our C side, right? And so for the Pythagorean theorem, we would just do like we have before, a squared plus b squared equals c squared. And in this case, a would be 5, b would be 1, 2, 3, 4, 5, 6, 7, 8. And then we could just figure it out from there. We would get 25 plus 64 equals c squared. So we get 89 equals c squared. Then we need to take the square root of both sides because square rooting is the inverse operation of squaring. And getting my calculator here, we have the square root of 89 is 9.43. And that's one way we could find the distance between those 2 points. And it's kind of cumbersome because for a couple reasons. Number one, I have to have the points on a grid. I can't just have the names of the points like, what is that? 1, 2, 3, 4, 5, 6, 7, 1, and 2, 9. It's cumbersome because I have to make the drawing and do all that stuff just to be able to get the information I need for the Pythagorean theorem. And so what we're going to look at today is an alternative to the Pythagorean theorem. We're going to erase this now that we've done the Pythagorean theorem, and we're going to go back to just having those 2 points. And we're going to be thinking about, is there a way that I could find the distance between those 2 points without making a triangle? So the first thing we need to do is 4, 5, 6, 7. Recognize that these points have names. That is point 7, 1. And the other point is point 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 0.71 and 0.29. And it's interesting because if you think about what we did with the Pythagorean theorem, when we made the A side across the bottom there, we came across there with that, right? And instead of counting boxes, we could have just done 7 minus 2. And that would have given us 5, just like we had for the Pythagorean theorem. And so I'm just going to write that down and say, hey, to get A, I could have done 7 minus 5. And that, or sorry, 7 minus 2, subtracting my x values. And that would have given me 5. The other piece I notice is that the 5 has to be squared for it to work on the Pythagorean theorem. So we're just going to copy that over here and make it squared. 1 second. Okay, I had a brief interruption. I'm back. And so we can do the same thing with the y values. It's going to be a little bit trickier, but and we'll talk about why. So if I copy the Pythagorean theorem, right, and we say, hey, look, that 7 minus 2 squared is exactly like what I would have had for a squared, because 7 minus 2 is 5, and I had 5 squared on the left, right? And let's keep going with copying the Pythagorean theorem and see what happens. And so the Pythagorean theorem then has a plus sign, and then it has the b value, which would have been our vertical value when we made our triangle earlier. And to find the vertical distance, the way that we would end up doing that is, in this case, and this is going to be a little bit weird because it's going to make a negative number, we would have 1 minus 9. Or we could go the other way and do 9 minus 1, just for the purpose of this demonstration. And that's going to be our b value. 9 minus 1 is going to make 8, just like we had 8 on the left. And that also has to be squared, so we got to make sure we copy the squared. And then instead of c squared, since we're talking about the distance between those 2 points, and we're not talking about a triangle, we're actually going to call this d squared instead of c squared. And so what I'm hoping we're able to see through this demonstration is that I have recreated the Pythagorean theorem in a little bit different form, and I don't need a triangle. All I need is the value of those points. And so again, the 7 minus 2 is the horizontal distance, which is 5. So let's match these things up. The 7 minus 2 goes with the 5. And the 9 minus 1 goes with the 8. And the 7 minus 2 is squared, just like the 5 was squared. The 9 minus 1 is squared, just like the 8 was squared. And then lastly, the d squared goes with the c squared. And so I'm hoping that you're able to see the similarities between what we're calling the distance formula and the Pythagorean theorem through this illustration. And then we're going to continue and go ahead and move on with finishing up this distance formula thing and see what we get. So we're going to get 7 minus 2 is 5, still squared, plus 9 minus 1 is 8, still squared, is equal to d squared. And so we get 25 plus 64 equals d squared, just like we did over there. And then we're going to have 89 equals d squared, exactly like we did over there. And then we're going to take our square root. Again, the inverse operation of squaring is to take the square root. We get 9.43 equals d. So the distance between those 2 points is 9.43. We can do that without using the Pythagorean theorem and just using the distance formula. So what we're going to do next is I'm going to leave this here for a moment to pause if we need to. I'm going to erase everything. And we're just going to talk about the distance formula by itself and kind of what it is and how we can create a formula that will work every single time. And so if we are looking for the distance between the horizontal distance here, between those 2 points, it's helpful if we name these points in unique ways so that we can call them out by name. Because if I just called this x and I call that y and I call this x and I call that y, if I say x, which one am I talking about? The 2 or the 7? Well, I don't know. And if I say y, which one am I talking about? The 9 or the 1? I don't know. And so what we need to do is give them unique names like x1 and y1 and x2 and y2. These are not squared in the bottom right. It is a sub 2, meaning it floats a little bit below the line on the page. And so it's just a way for us to be able to tell which x and which y we're talking about. Again, we're going to call x1 and y1 those values up there, and x2 and y2 those values right there. Now if we match it up to what we did a minute ago, we did 7 minus 2 to get the 5. And so instead of 7 minus 2, I'm just going to write x2 minus x1. Actually, let's rewrite what we had previously, and then we'll be able to tie it all together. So we had 7 minus 2 squared. And then if you remember, I said it was going to be weird if I did 1 minus 9, but we did 9 minus 1 instead. This time I'm going to stick with my 1 minus 9. And we're going to replace these numbers with our x's and y's. And so 7 minus 2 would be x2 minus x1. Still have it squared. The 1 minus 9 is y2 minus y1. Still squared. Equals d squared. And so this right here is what we call the distance formula. And we can use that to find the length between points on a grid without having to make a right triangle. But it is exactly related to, again, as we demonstrated a little bit ago, this is the same as my a squared, plus this is the same as my b squared, And then the d squared is just replacing the c squared. And so this is the Pythagorean theorem written a little bit differently and not requiring a triangle to be able to do the work. We can do this just by going off of the x and y values of points that we are given.